Hi everyone, welcome to Shannon Channel Talk. I'm really happy today to have Po-Ling from Wisconsin-Madison, and she's gonna give us a talk on statistical inference for infectious disease modeling. Thank you, Po-Ling.
Okay, well, thank you very much, Salim, for the introduction. Let me just pull this up quickly. Okay, great. So yeah, this is joint work with my student Justin Kim, who is finishing up his PhD at UPenn, and he's in the statistics department. So my talk is going to proceed in two parts, and it sort of talks about two different questions. And we are motivated by the question of how we can use statistical techniques in the presence of data that come in the form of a network of some kind. So the first part of the talk is sort of talking about estimation and confidence intervals. And the second part of the talk will be about hypothesis testing. Okay, so the question that we're going to be looking at is a question of source estimation. So imagine you have some kind of a network, and you have a disease or some information that's propagating over the network in a contagious manner. So what that means is that at the beginning of time, you have one node that is infected, and on successive time steps, there is some neighboring node that's chosen as the next node to be infected. And this behaves according to some kind of a probabilistic process. And in particular, we look at the case where the next neighbor is chosen uniformly at random from amongst all of the neighbors of currently infected nodes. So the way that we've drawn this picture, it's arranged into a nice tree so that the first node to be infected was at the top. But in practice, you just have a bunch of individuals who are connected in some way, and you observe it at some snapshot of time. And it's not exactly clear what the original node would be. All right, so sort of to reiterate, what we're given is a single snapshot of a bunch of individuals who are all infected. What we know is that the disease propagated according to contagion over some tree or some graph that we observe. And we want to infer where the first node to be infected was. So actually, instead of just looking at one node, what we'll be looking at is to find a collection of nodes so that with a certain probability, the collection contains the source. And the reason for wanting to pick one node rather than, the reason for picking several nodes rather than just one node is that, for instance, if you have some kind of a regular tree, so it's just fully symmetric and every node has the same number of vertices, and let's say you look at a snapshot of time that's the second stage of the infection, then everything is fully symmetric. And so whatever procedure that you have for picking out one node will have probability of success bounded by 1/2. And so for this reason, as I said, we want to pick out a collection of nodes rather than just a single node, because we want to be able to guarantee that, let's say with probability at least 95%, the estimator that we construct will contain the source. Okay, so here's the picture that we have some snapshot of time. We know who's infected, and we want to know how can we construct some kind of a set based on our observed infection information. And I should say that the way that we've drawn this picture, we've sort of circled the nodes that are all towards the center of the graph, and that's exactly what your intuition would tell you, that somehow you want to identify nodes towards the center of this spread, because those are most likely to be the first ones. Another thing is I've drawn it in such a way that the nodes that we pick out to be in our set are all connected to each other. However, this is not necessarily, it doesn't have to be the case if we're just trying to pick out some set of probable nodes. As it turns out, the estimators that I'll describe do in fact give you a contiguous subset of nodes. Another thing to note is that, as I said, we're trying to do statistics on a network. And the statistical setting here is that instead of looking at just a single estimator, we're looking at an entire set of estimators. And that's kind of the analog between a point estimator in statistics and a confidence interval. The confidence interval is where we can pick out some continuum of points rather than just one estimator that's like a maximum likelihood estimator, for instance. All right. So of course, a very silly estimator would be one that just selects all of the red nodes, right? Because if we want to say that with high probability our estimator is correct, then we could just pick out all the nodes. But that's not too exciting because, of course, we sort of want to use a minimal set in some sense. So we also want to know, for whatever estimator that we might describe, how does the size of this confidence set have to grow as the number of nodes increases? And by number of nodes increases, I basically mean that we have some kind of an infection and then we let it propagate even further. So the interesting conclusion that we drew was that, in fact, the size of this set does not have to grow. So this is, well, a couple comments on this. So first of all, this is not sort of a universal statement. Obviously, it depends on the manner in which the disease is propagating. And the way I set it up, I said, well, we have some nice tree structure. We have some nice symmetry, like it's a very regular tree. And the next node to be infected is chosen uniformly at random amongst the boundary of all previously infected nodes. So subject to those spreading conditions, then this conclusion is true. So subject to those spreading conditions, it is in fact true that the size of the confidence set doesn't have to grow. However, one might imagine dreaming up some other infection spreads that spread much, much more quickly. And in those probabilistic settings, it may well be that the size of the confidence set has to increase as the number of infected nodes increases. All right. So now I'll describe the estimators that we studied. So at the top, it's a math equation. At the bottom, I'm going to try to illustrate it using pictures. So what this is saying is that we are going to compute this criterion psi of u for every node in the graph. And the way that we compute it is we look at a particular node u, and then we look at what would happen if we disconnected u from all of its neighbors. So what we imagine is that you take away all the edges connected to u, and instead of having a tree, a red tree, you have a red forest, because that separates the tree into several subtrees. And now for each one of those subtrees, you want to count up the number of nodes in that subtree, and you want to look at the maximum amongst those subtrees. In this case, there are 3 subtrees, and the bottom right one is the largest. So the value psi of u is going to be equal to 8, because that's the number of nodes that were in that portion. And then you go and you compute this criterion for every single node in the graph. So you get something like this. And something to notice is that, in fact, the smallest values of this criterion are towards the center of the tree, and the largest ones are kind of further out. Another way to see that is if you were to compute the criterion for a node that was a leaf, then the value of this criterion would be n-1, where n is the number of nodes. And that's simply because you disconnect that node from its neighbors, and you still have a tree, and that tree has the same number of nodes as before, -1. And so as we can see, the periphery of the tree will have larger values of the criterion, whereas the middle of the tree will have a smaller value of the criterion, simply because it's breaking up the tree into lots of different parts. Okay, so it turns out that if you calculate the minimal node that minimizes this value, you'll actually get something called a tree centroid. So the tree centroid is, it's just a notion in graph theory. And actually, one characterization is exactly what I said. Another characterization is that it's the node that, if you sum up all the distances to all other nodes in the network, then it's minimal. So there are several different characterizations of a tree centroid.
Is it the tree centroid of everything, or just the red tree?
It's the tree centroid of just the red tree, because we're only calculating these things with respect to the red tree.
Can you also remind me a little bit about, what is the model of this? Is it block cascade or these standard models, or is it a different model?
It's a very simple model, and so the model is simply that there's a node that's infected at time 1, and then at each successive step, you infect exactly 1 node, and that node is chosen uniformly at random from the neighbors.
Okay.
Right, so there's not really a cascade going on. I guess in the usual information cascade, for instance, or independent cascade models, then every infected node has a chance to infect any of its neighbors on each step. And so I mean, you could have multiple neighbors being infected on a particular time step. Whereas here, we're just picking 1 node.
And here is a node that was not infected in the first maybe step could be infected in the second one.
Yeah. So if we go back to this illustration, right? I mean, you can imagine, well, so if we go from here to here, then that could mean that the guy on the second level was not infected on that particular step, but then on a successive one, it might be.
Okay. Yeah. All right, thanks.
Okay. Right. So this is a method. This is a criterion by which we kind of give a score to every node in the graph. And as I said, though, we want to pick not just one node that's sort of the most likely, but we want to pick some subset of nodes. So our estimator, our confidence set, is to say, well, we just want to pick the minimum k of epsilon number of nodes, where k is a function that we're going to say a bit more about later. All right, so the statement is that for a particular k that I'm going to describe, that depends only on epsilon and not the number of red nodes, then if we construct this set as the minimal guys that minimize this criterion psi, then we in fact get a valid estimator. So the valid estimator means that with probability at least 1 minus epsilon, this estimator will be correct. So it will contain the source. Okay. So then there's one other estimator that I'm going to discuss. And the second estimator is based more on maximum likelihood. So you might imagine that if you want to figure out the most likely node or nodes that could have started the whole infection, you could write down something along the lines of maximum likelihood. In this case, it's actually not too hard because the process is so simple. So we had a tree to begin with. Furthermore, I think I might not have said this too clearly, but it's a regular tree, which means that every node has the same number of neighbors, has d neighbors, let's say. Then you can just sort of easily write down the probability of any particular infection path happening in the tree. And then you can figure out how to calculate what is the maximum likelihood estimator for the first node that would have started the cascade. And it turns out that it has a particularly simple form. So again, I'll illustrate it in pictures. So what we want to do is calculate a criterion phi, and this criterion is going to be somewhat different than the previous one. So we're going to call this one phi, and the other one is psi. So for the phi estimator, what we take is a product of trees. And now instead of just taking the product of these 3 trees that I've circled, what we actually want to take is the product of all subtrees in the graph that are originating from any node. So the picture is here. So instead of, you can think about the large chunks as being originating from the neighbors of U. And then for any other node in the graph, you create a tree that's sort of pointing away from U. And so I've tried to circle that in this graph. So you have a whole bunch of smaller subtrees. Each one is originating from a different node in the graph. You multiply all these things and you get some large number. So I calculated it here just for that middle node. It's some large number. And I think I didn't bother calculating it for the other nodes. But again, the basic idea is we want to calculate this for every node in the graph. And we want to look at the minimum value of that criterion, and or the minimum several values. So it turns out that if we calculate just the minimum, the one minimum node, then not only is that the maximum likelihood estimator, because that's how we set it up, but it's also going to coincide with the tree centroid of the graph. And however, if we now pick out some set k epsilon of nodes with minimum values, then let's say the 5 minimal nodes according to the phi criterion are not in general going to agree with the 5 minimal nodes of the psi criterion. But the claim is that in fact this will also give you a valid confidence set. Okay. Another thing to just sort of to note in passing is that one might think that that this second criterion is really hard to compute because the numbers are way, way bigger. But from the point of view of computational complexity, it turns out that you can evaluate both phi and psi over the whole graph in order n time, where n is the number of red nodes. Maybe it's sort of easier to see in the case of this min-max subtree estimator, because in some sense the criterion is trivially computed on the leaves. It's just n-1 on all the leaves. And then you can kind of think about sort of linearly, in some sense, passing through the whole graph to calculate all of these values, ranking them and picking up the top 5 or 6. In the case of the second estimator, where we're multiplying all these tree values and it gets much bigger, It's maybe not so obvious, but this type of estimator was also studied in some previous work by Shah and Zeman. And in that paper, they showed that, in fact, you can also calculate the second criterion in order n time using a slightly more sophisticated message passing algorithm. So this is just to say that from the point of view of computational complexity, the two types of estimators that I described, neither one is better than the other. Okay, so now here's the theorem. And the theorem basically says that this works. So let's kind of parse out why it works. So basically it's saying that that if the number of neighbors of each node is at least 3, and we'll talk about the d equals 2 case in a moment, then in fact we can get a 1 minus epsilon confidence set for the source node if we choose the k function to be what's listed on this slide. Okay, so I don't want you to really stare at this too much, but the most important thing is that these two functions are functions only of epsilon. So remember, it's saying like if we want a 95% confidence set, it doesn't matter whether the number of red nodes is 10 or 10 million. All right, all you need is, let's say, 5 or 6 nodes. So the other mystery constants, well, there's a C and there's an A and there's a B. These are all functions of D, of the number of neighbors of each node. So maybe just as a, well, let me skip that thing for now, but just as a quick illustration. So imagine we're looking at the case where D equals 2. So when you look at this theorem, one thing you might ask is, why is D at least 3? Well, let's imagine we're looking at a case when D equals 2. So remember, D is the degree of the underlying subtree. In this case, if the number of neighbors of each node is 2, the underlying subtree is just a line. And what happens is that on each successive time step, one of the two end nodes, which are not infected, will get infected with probability 1/2 each, because we're always picking a node uniformly at random on the infection boundary. All right, so in some sense, it's kind of like a random walk on a line. It's either going to the right with probability 1/2 or going to the left with probability 1/2. And it's not too difficult to see that actually the minimum confidence set that will contain the root with probability, let's say 95%, it actually has to grow with n, the number of red nodes. In fact, it has to grow as square root of n if you want to guarantee that with a certain high probability you're containing the source. So this is in contrast to the theorem. So the theorem says that if you're not spreading on a line, but you're spreading on some sort of regular tree, let's say every node has 3 neighbors or 4 neighbors, then this sort of information diffusion, if you will, is not happening. All right, so whereas on the line, things are sort of spreading so quickly that any confidence set has to have growing size, in some kind of a tree that looks more like this, then the information is sort of diffusing, but not that quickly, so it sort of remains concentrated near the centroid. So then the other statement on this line on a slide was just to say, let's compare k phi to k psi. We didn't really show lower bounds on anything, but I guess this is sort of just a sanity check that, note that these are both sufficient conditions. It's saying that if you choose k psi nodes with a psi estimator, then you're guaranteed a 1 minus epsilon confidence set. If you choose k phi for the phi estimator, you're guaranteed a 1 minus epsilon confidence set. And it's just sort of a quick check that, in fact, the guarantee is a little bit stronger if we allow ourselves to use the maximum likelihood estimator. And so, in fact, you can compare these two expressions and see that that k phi is smaller than k psi. Okay, so then a comment on some related work. So there is a bunch of work from Devarat Shah's group, I guess Shah and Zeman, maybe 7 years ago. And they were looking at these types of problems in the context of gossip or rumors spreading over a graph. So I mentioned their work earlier because I said that they had shown that there's in fact an order n algorithm for evaluating all of these maximum likelihood functions over all the nodes. So in their particular work, they were interested in sort of finding a point estimator. So they wanted to find one node, which was the maximum likelihood estimator for the source of the graph. And they wanted to know what is the error probability of this particular node. And they were also looking at these d-regular trees where you have information propagating over a regular tree. We were motivated by some more recent work out of the probability theory community. So this is Sebastian Bubeck, Luc Devroy, and Gabor Lugosi. And they were looking not at information spreading over a fixed network, but at information spreading kind of as a network evolves. So there are these notions of preferential and uniform attachment in the network science community. And basically, this is a model of network evolution. So what they're trying to do is describe some kind of a network structure that you might observe in a Facebook graph. So something perhaps like this. And they're asking, well, what is some method that by which this graph could be realized if we start from one node and we build it up? So the two models of attachment are preferential and uniform. And the difference is just the probabilistic rule by which new connections form as a new node comes in. So in uniform attachment, we just say that every time we add a new node, it attaches to an existing node with equal probability. But what happens in preferential attachment is that a new node that comes in looks at the degrees of the existing nodes. It's like it looks at how many friends each node has. And if that node has more friends, it decides that that node must be more popular, so it's better to attach to that. So if this next node were to come in, it would say, well, the middle node has twice as many neighbors as the edges, as the other ones. So with probability 1/2, I'll attach to the middle node. And with probability 1/4, I'll attach to any of the others. And so then this thing propagates. And so what we find is that, in fact, in these preferential attachment models, we have a sort of power law degree distribution. And this is quite interesting in network science because they find these types of distributions in real world networks. Okay, but in the probability theory community, what they were interested in is if you see a graph that looks like this, and you know it came from preferential attachment, then how do you come up with some estimator for what the source was? All right. So it has some flavor of the Shah and Zeman work, except instead of having information spreading over a known network, you have a network that's growing. And they called this sort of work finding Adam, because it's like finding where the source of everything came from. And in their work, they were also looking at these two criteria. So instead of looking to pick out one node, they were picking out a set of nodes. So sort of like in our work. So our work was motivated by the Bubeck et al. Work and partly also the Shah and Zeman work. We were combining the two of them and trying to understand how we could construct these sorts of confidence sets if we have information that's propagating over a fixed network. All right. So now I'll say a little bit about the proof. I'm not going to say too much. I guess I just want to show some pictures and give some rough intuition. So the main proof technique here is to use this notion of polyerns, which I'll introduce / review very briefly. It might not be immediately obvious what this has to do with the graph, but let me just explain how a polyern works and then relate it back to the graph. So a polyern is basically a box of balls of different colors. And it's sort of a process that evolves. So on each successive time step, someone will pick a ball at random amongst the balls in the urn and look at the color and then replace it in the urn together with balls of potentially the same color or different colors. And the replacement rule is governed by a replacement matrix. So for instance, if the rows of this matrix correspond to yellow, green, red, and blue, then the replacement matrix is saying that whenever you draw a yellow ball, you return it to the urn together with A yellow balls and no balls of other colors. If you draw a green ball, you'll return it to the urn with B green balls and no balls of other colors, and so on. But you might imagine a setting in which this matrix is not diagonal and is fully dense, and that basically says that you look at if you get a yellow ball, you replace it to the urn with A1 yellow balls, A2 green balls, A3 red balls, and A4 blue balls. So in probability theory, people have studied these types of urns, and one useful fact which we use in our work is simply telling what do the limiting proportions look like. All right, so what I've written on the left side, this simply denotes the number of balls of each color, yellow, green, red, and blue. And it turns out that this converges in distribution to a Dirichlet distribution. And this is the case if our matrix is in fact diagonal, and not only is diagonal, but is a multiple of the identity. And the dependence on the initial conditions is just that the parameters of the Dirichlet distribution depend on the initial states, the number of yellow, green, red, and blue balls, which are A0, B0, C0, D0. There are similar types of results that people have proven in probability for urns where the replacement matrix is not diagonal, but they get more complicated very fast. So there's this notion of a balanced urn where the sum of the entries in each row is supposed to be constant. Of course, this is a balanced urn. But if you want to have more complicated formulae, this is what happens when the urn is not balanced, or when you might even have negative numbers, and that corresponds to taking some balls out of the urn of certain colors if you draw a particular color ball. Okay, so what does this have to do with this problem? So let me maybe skip some slides briefly and just look at a picture. And so this is more or less what the urn has to do with our problem. So in some sense, our estimators depend on the centrality of nodes, right? So we look at kind of, for instance, if we're looking at this min-max subtree estimator, we're calculating the number of nodes of different, the number of nodes that are infected for different branches in the tree. And the hope is that sort of the centroid of the infection doesn't move around too much. So at time t equals 1, clearly the first node is the centroid of the infection because there aren't any other nodes. As the infection propagates, the hope is that things don't move too much in one direction on one branch of the tree, because if so, then these centrality-based estimators would be really, really far from the actual root. So what we want to analyze is kind of the relative growth of the infection on different branches of the tree. And it's not quite enough to just look at the relative growth from one particular node, but it turns out that it's enough to look at the relative growth from the first capital K nodes, where that's the number of nodes that we're proposing to put in our confidence set. Okay, so if you believe that, then it's enough to sort of look at how these green, yellow, and blue branches behave. And I've colored these suggestively in such a way that they reflect what happened in the polar urn. So just to reiterate, earlier I was drawing red nodes, and the union of all these nodes should be red. These are the infected ones. Those are the ones we're counting. And I've just sort of colored in different branches to reflect the polar urn. So at a particular time step, this is what the network would look like. And now you can imagine what would happen on the next time step. So the next time step, some node is going to be infected, uniformly chosen at random from the boundary of all the nodes that are currently infected. And because this graph is deregular, so every node has the same number of every node has the same number of neighbors. It turns out that the number of nodes on this infection boundary is proportional to the number of nodes of that color in this infection process. So the probability that the next node to be infected joins to the green branch is proportional to the number of green nodes, and similarly for yellow, and similarly for blue. So in other words, if this yellow tree is substantially larger than the rest, then it's much more likely that the next node will join to yellow. And that's exactly where the analogy to the polar urn process is. Because if you remember, the polar urn process was drawing a bunch of nodes, drawing a bunch of balls of different colors from a box. And if there are more yellow or red nodes, then they're more likely to be picked next. And the fact that this replacement matrix is diagonal, is a multiple of the identity, is exactly what I said. Because it's a deregular tree, the probability of joining to the boundary of a particular color is exactly proportional to the number of nodes of that color. Now, if you look at this picture more critically, you'll realize that it's not exactly accurate. And the reason it isn't is because no nodes will ever become red, because this red node, according to the picture, is sort of fully saturated. All of its neighbors are already infected, so any other node that's infected will never become red. So actually, the way I should be drawing this picture is slightly different. It's like this. And here I'm just coloring the neighbors on the infection boundary of each tree. And if we go back to our polar urn analog, it simply says that at this point in the urn, the red color was already exhausted, so you'll never get any more red balls after that. Okay, so that's kind of the intuition for how this is analyzed. The details are sort of just details, and so maybe I'll just kind of, well, I'll put up these lines very quickly just for general interest. So what we want to do is we want to bound the error probability by epsilon, right? I mean, that's what constructing a confidence set estimator means. It means the probability of being wrong is bounded by epsilon. And as I mentioned before, it sort of suffices to track the relative centrality. So we think about psi as this measure of centrality, and we're picking the minimum k guys. It suffices to just track the first k guys. And so, well, we can argue that the probability of error is bounded by something that compares the centrality of node 1 with other nodes in the graph. And then if we, okay, I don't know how much into detail I want to do this, but so if we sort of manipulate these expressions, then what can happen is we're going to replace the psi criterion, which is sort of hard to analyze, with different subtrees in the graph. So I've sort of pictorially represented here what sorts of subtrees we need to be analyzing. So the expression we want to control has these values psi, which are hard to analyze because they have to do with the min-max of lots and lots of trees. So for the first term, if we can find an upper bound that's in terms of 2 trees that we can control, then we replace it with that. And then for the second term, if we can lower bound the psi criterion with something else that depends on certain other trees, then we can replace it with that. So that's sort of the general idea. So we take this expression that we want to bound by epsilon, we sort of turn it into something that just involves trees, and then we, at the very end of it, what we want to do is take the limit of these relative sizes of trees. So I'm not exactly sure how well this came out, but the basic idea is we have an expression for the probability of error, and we want to show that it's bounded by epsilon. So we're going to keep on bounding it with stuff that we'll eventually say is less than epsilon. And the stuff that we were looking at is going to depend on the relative sizes of different subtrees in the infection graph, which we can control because of this Polya-Ern analysis that I outlined. Okay, so once we get it in the form of this middle line, then the nice thing is that if we simply take a limit, then the relative sizes of subtrees, which are sort of hard to analyze, they simply turn into tails of a Dirichlet distribution, because we know that in the limit, everything converges to a Dirichlet distribution. So then it's very easy to answer, well, what should k be? Remember, k is the size of the confidence set. So we want to say, how big should k be so that this thing becomes less than epsilon? Because that's the probability we want it to bound it by. So that's the basic idea. I think the last thing I wanted to say here was that we take limits and we integrate the probabilities to figure out what k should be. And when that is all done, then we conclude that, in fact, I think I have a theorem somewhere here. Yeah, so we conclude that, in fact, if we choose k to be something like something to the d over epsilon, then this error probability will, in fact, be bounded by epsilon. All right. So that's, I think, the first part of the talk. And what we did was we looked at different estimators that can give provable confidence sets for this sort of infection process growing over a graph. We have some small extensions. So the setting that I described, we have a d-regular tree, so every node has the same number d of neighbors. Another natural situation you might want to look at is where you still have the same regular structure, but instead of every node having d neighbors, you might draw the number of neighbors from some fixed distribution, and that would be a Galton-Watson tree. So we showed that in that case, in fact, you can also get some finite-sized confidence set that doesn't have to grow as the number of infected nodes grows. But then there's a lot more work to be done. So we've thought about this a lot. We haven't really been able to say much about anything else. So the hunch is that whenever you have some kind of regular or uniform spread in all directions, then probably some kind of a confidence set that's calculated in terms of these centrality notions should work. However, the difference is that because our analysis depends so critically on this Polya-Ern stuff, and the Polya-Ern analysis is really sort of this discrete probability theory saying, well, does a new node join to one branch or the other? It doesn't quite carry over to any other type of infection process that one might want to look at. So some other infection processes that people study are these sorts of independent cascade models or SIR models, and we don't have any theory for that. Another important direction would just be looking at non-trees. So for instance, if you have an infection that's spreading over a lattice, a 2D lattice, for instance, then you would hope that the same sort of centrality notions would also give you a confidence set. But again, the problem is that our polar urn analysis doesn't work because these different branches in the tree sort of are colliding with each other, and the same type of analysis won't work. We were kind of thinking about looking at Galton-Watson trees because we wanted to analyze Erdős-Renyi graphs, which are locally Galton-Watson. Unfortunately, after handling the Galton-Watson case, we weren't able to extend anything to Erdős-Renyi graphs. Okay, so that's the first part. Does anyone have any questions?
I think no questions.
Okay, all right, I will keep going then. Okay, so the second part is also having to do with infection spreading on graphs. The difference here is that, well, we were looking at some notion of hypothesis testing. So the first part was sort of confidence sets, confidence intervals, etc. And if you take like a statistics 101 class, the other thing you learn about is hypothesis tests. So we were just sort of wondering what kind of hypothesis test stuff could we explore in the world of graphs. Okay, so the problem setting here is that we have some different graphs that we hypothesize might be responsible for governing how an infection is spreading. And the question is, if we have information about who is infected, then can that help us distinguish between different possible network structures? So in this setting, I mean, so you might imagine that the first one is that everyone is equally likely to give or receive infection from each other. The middle one is that there's sort of a hub. So maybe if the infection is like some information, then it simply means that everyone talks to one person, but not really so much to each other. And so what we have is just one snapshot of information on who has the disease. And we want to infer which one of these structures is sort of most likely. So the way I've drawn it, if the information is going to spread through contagion, then the second one is extremely unlikely or just impossible, because if the information starts from a single node, then it's going to have to go through that hub node before it gets to anybody else. Okay, so to make things a little bit more interesting, and to make it so that the second picture wasn't automatically impossible, we looked at a setting where we might also have censoring. So in addition to knowing definitively that nodes either have the information or don't, there's also going to be some subset of nodes that are grayed out, which means that we have no idea whether they are infected or not. So for instance, now the middle picture, it might actually be possible that information spread on this graph because we don't know whether the hub node had the infection or not. So the notation that we'll use is that the number of nodes that we know are infected is K, the number of gray nodes is C, and then everyone else we know is uninfected. Okay, so remember, for hypothesis testing, we want to figure out some kind of a test statistic, and we want to figure out some kind of rejection rule so that under the null hypothesis, the probability of error will be bounded by something that we want. So in order to actually derive some kind of reasonable hypothesis test, we need some explicit probabilistic manner in which information is spreading over the graph. So here's where the model is described. So basically, we have a bunch of independent exponential random variables, and these are waiting times until some sort of infection event occurs. So we have an exponential random variable corresponding to every node in the graph, and that's just the amount of time that node should wait before it becomes infected. And then on every edge, there is also an exponential random variable that is independently and identically distributed with parameter eta. And that's simply the waiting time after which a node will become infected once its neighbor becomes infected. So then the time at which a particular node gets infected is going to be the minimum of when it would receive the infection just by sitting by itself, or the if any of its nodes became, if any of its neighbors became infected and then infected it, t sub uv time later. So the reason why we have this this random variable tv for every node is, well, you could say maybe there's some kind of way in which someone can get the infection just from the air, just from being in the community. Or another interpretation is that these edges sort of correspond to patterns of connection that you think exist in the community, but then there might be some sort of exogenous ways in which nodes become infected or receive information that aren't captured in the graph itself. So it's like there is a fixed graph through which most of the infection is happening, and then there's also some other exogenous source that that gives rise to this extra waiting time for every node, through which the node could become infected just by sitting there by itself. Okay, so then the observation vector, well, I say vector, but really it's just the figure of who is infected and who is not. So that corresponds to the infection states at a particular time step. And furthermore, we assume that the censoring is chosen uniformly at random. So think about it like there's an infection and it grows out to a particular time when there are n nodes that are infected, and then some subset of nodes are censored uniformly. Okay, so as I said, the trick with hypothesis testing is to figure out a reasonable test statistic, and then to figure out a reasonable rule, and then to prove that it works. So a test statistic that we thought of, and there may be other ones that also make sense, but this one seemed natural, is that you look at the nodes that are infected in your hypothesized graph. So you'll see that in all three of these graphs, it's the same configuration of who's infected and who's not. The test statistic consists of figuring out how many connections there are within red nodes in the graph. So in this clique, we have a very large number of connections, t equals 10. In the star, it's 0, which doesn't seem quite so likely, because you would sort of expect that if infections are actually spreading along the edges of the graph, then probably the red ones are pretty well connected within the graph that you're looking at. And then the one on the right is somewhere in between. So there are some connections between red nodes, but not a whole lot. So the test statistic that we looked at is simply the count of the number of blue lines, the edges between infected nodes. All right, and then what we need to do is we need to figure out a proper rejection rule based on t. So we want to say if it's above or below a certain threshold, then we'll reject the null hypothesis. Okay, so here is just sort of a slight reformulation. So remember that in hypothesis testing, we want to bound the type 1 error, which is the probability that given the null hypothesis is true, the probability of rejecting the hypothesis is going to be bounded by alpha. Okay, so how do we come up with a proper threshold? Well, what we decided to do is something based on permutation testing. And let me describe what permutation testing means. Well, basically, what we have, so let me remind you, what we have is just the figure on the left. So the figure on the left is telling us, well, we have a particular graph that we're hypothesizing, and we have a bunch of nodes that are infected, and that's it. So what we want to do with that is figure out some kind of a rejection rule. And if you remember from basic statistics, getting a rejection rule basically consists of looking at some kind of a distribution and looking at the alpha quantile, right? So the problem here is that this is really complicated and we have no clue what the distribution looks like, so we don't know how to pick out the alpha quantile. So permutation testing is this trick of sort of saying, well, I only have one data point, and what I'm going to do is I'm going to kind of generate some synthetic data sets by simply repermuting the labels of everything. So in this case, I have 5 red nodes, 2 gray, and 1 white. So I'm just going to arbitrarily look at all of the possible reassignments of red and white and gray that preserves the number in each category, and reassign all of these nodes, and then recompute my test statistic. So for the first one, for the data I actually had, it was 0, but then for the other ones, it's 4. And in general, it's going to give you some empirical distribution. Right. So then the way so the way permutation test works is it says, well, I'm going to figure out what the rejection region should be based on this empirical distribution. So after generating all of these repermutations, I get my alpha quantile. And then the question is, do I accept or reject the null hypothesis? Well, I go back to my original situation, and I see that my t was equal to 0, or whatever it was. So then I go and look at where that t is, and if that test statistic is below alpha, then I don't reject, and when it's above that alpha quantile, I do reject. And so that's the basic way in which permutation testing works. And it is, well, it kind of comes from this notion of exchangeability. So the basic idea is I want to understand, how this test statistic behaves if under the null hypothesis, right? Because the idea is that there's some null hypothesis, and I want to just look at possible extreme tails and understand what that looks like. And so the basic idea is that if the null hypothesis is in some sense exchangeable, so that means that it really doesn't matter what permutation I put on the red and gray and white things, then this sort of permutation testing will in fact give me sort of a faithful representation of what the distribution looks like under the null. And so that's why this works. Okay. Then also for permutation testing, well, not too surprisingly, if I wanted to compute some kind of an empirical distribution based on all possible reassignments of nodes, I probably only need to do it for some very large number of permutations. So it's not actually necessary to look at all possible n choose whatever it is, n choose k, c, n minus k minus c reassignments. Okay. So I think I am going to say a tiny bit about the proof in a little bit, but maybe let me try to sort of, maybe say a little bit in terms of motivation and in terms of words exactly what our result is. So I kind of hinted at the fact that there's some exchangeability going on. And in some sense, maybe it wouldn't be too surprising if I told you that this will always work if the null hypothesis is an empty graph or a complete graph. Because if the null hypothesis is that everyone sort of communicates with everybody else, then under the null hypothesis, it really doesn't matter how I permute whatever I want to do. Similarly, if the null hypothesis were an empty graph, then everyone is completely exchangeable with everybody else as well. The challenge in this work was to show when this permutation test is actually valid in settings that go beyond the case when you have a completely empty or a completely full graph. So our theoretical result really depends on something that has to do with what these graph topologies look like. And in particular, it has to do with automorphism groups of the graph. So let me remind you what an automorphism is. A graph automorphism is a permutation of the nodes in a graph that preserves connectivity of edges. So I've given you one example of an automorphism where I fixed 1 and 2, but then 3 and 4 I flipped, because as long as they're still connected in the mapping, then it's fine. And then for the remaining nodes 5, 6, 7, and 8, I permuted them in some arbitrary way. So in general, the set of automorphisms of a graph is going to be a subgroup of the permutation group Sn. Okay. So the theorem that we have is basically, well, let me put it in the next slide. So the theorem that we have is that the permutation test succeeds whenever the product of these two automorphism groups is equal to the full permutation group. So just as a simple illustration, so I was saying before that if the permutation, if the original graph were the complete graph, then this method should sort of intuitively, trivially work out. So in the case when the graph G0 is the complete graph, then the automorphism group is going to be all of Sn. Because remember, automorphisms just have to preserve connectivity, and if everything is connected anyway, then any permutation is fine. And so if we go back here, well, this condition is definitely always holding, right? So if H0 is completely empty or completely full graph, pi 0 is equal to Sn, so then this permutation test always works. So the more complicated stuff is to understand what this looks like, what this criterion actually looks like when the graphs are not complete or full, when are not complete or empty. So just maybe, I don't know, I think I'll skip through the proof here, but the basic idea is to say that in order for this to work, I want to say that the tails of the test statistic are the same as the tails of the empirical distribution based on permutations. So if I advance a couple of slides, then what we see on the very last line is the tails of the empirical distribution, right? So it's sort of like a CDF where we look at one particular infection assignment and we look at all possible permutations and we look at the empirical distribution over all n factorial of them. So the math behind it is to get from the first expression to the very last. And you can do this by some sort of smart manipulation of things. But maybe let me leave it at that. So this derivation says that provided the criterion pi1 times pi0 equals Sn, then in fact this works because the tails of the distribution itself under the null hypothesis are the same as the tails of this empirical distribution that we generate using a permutation test. I should also say that permutation testing sort of comes up in introductory statistics in just one form. And the method that we use to prove that it works here is sort of very, very analogous to the classical method that people use to prove that permutation testing works in standard statistics. Okay, but I wanted to spend a bit of time maybe talking about interpretability of these conditions. So as I said, if the null hypothesis graph is complete or empty, then pi0 is equal to Sn. You can also see quite easily by looking at this mathematical statement that if H1 is a complete or empty graph, then pi1 is also equal to Sn, so this is always true. In general, it's going to be more difficult to understand what this criterion means. So we looked at a special case, and in this special case, we looked at one of the graphs being a star graph. And the reason why we did this is that in that case, the automorphism group is very easy to characterize. And automorphisms simply say that the middle node stays the same, and then any of the peripheral nodes can be interchanged however you want them to be, because the only thing that's preserved is that they're all connected to the middle one. So in that case, the automorphism group is Sn minus 1, and then it's not too hard to sort of play around with these graphs and figure out what are the criteria by which the product of automorphism groups of some other graph and the star graph is equal to Sn. Turns out that the criterion is that the other graph should be vertex transitive. And let me not go into detail there. So vertex transitivity is a notion in graph theory. And it turns out that it's a property that is held by graphs, including the family of Cayley graphs. And just as some simple examples, the cycle graph or a toroidal grid graph fall into this family. So all I'm trying to say here is that our method also works in the case when you're trying to test between, let's say, a toroidal grid graph and a star graph. Okay, so now the rest of the slides are sort of just sort of postscripts. So a few things that you might want to analyze are what's called the type 2 error. So the type 2 error says, well, I'm not just looking at the probability of error when the null is true. I also want to look at the probability of error when the alternative is true. And I want this to be small as well. So not surprisingly, our theory is very hard to apply in the most general setting to bound what the type 2 error looks like. So again, we looked at a simple case. So the simple case was motivated by the example I just went through, where you have a star graph on the one hand and something like a cycle graph on the other. And again, I don't want you to stare too much at this expression, but I just want to say something about how this expression depends on the two parameters of governing the spread. So if you remember, there was an exponential parameter lambda governing how quickly nodes get the infection just by themselves. And then there was another parameter eta governing how quickly the infection will spread over an edge. So what you would expect is that if eta is getting larger relatively to lambda, then most of the infections are happening over edges, right? Because it's happening at a much more rapid pace between neighbors than sort of just out of thin air. And so then you would expect that it's much simpler to distinguish two possible graph structures, because most of the infections are happening over edges anyway. So the sanity check is to look at this expression for the probability of error. And then it turns out that as eta gets bigger, the error decreases. So that's confirming exactly what we were saying, which is that since eta getting bigger means that graphs are easier to distinguish, then the probability of error should be decaying. And I'll come back to this expression in a moment in a different setting. Okay, so then the other thing was to understand what happens to this test if we observe more infection spreads. So just to make things a little bit more concrete, imagine that we have a bunch of individuals or a bunch of communities that are connected by, let's say, airline paths. So these let's say these nodes are cities, and the lines are telling us when air traffic goes between one city and another, and we're trying to trace some information that was spread only by an airline network. So we look at how it was spread last year versus the year before versus the year before that versus the year before that. Right? So it's the same individuals, it's the same connections, but a different spread happening over that same network. The question here is, if we observe multiple infection spreads, then can we still do a permutation test there? And well, it's not too hard to show that, in fact, the same sort of stuff works. So what would the permutation test look like? Well, the test statistic would probably be the average of all of these edges within statistics. So now it's like we observe 4 at a time, and we count up the total number of edges between red nodes in any of these graphs, and we average it out. And then to get the overall distribution in order to do a hypothesis test, we do a similar permutation test where we just reassign everything for all 4 replicates. So the theory, it's not too hard to show that this works. Maybe the slightly more interesting thing is to relate this back to the type 2 error. So this type 2 error, the probability of being wrong when the alternative is true, should hopefully get even smaller as m gets bigger, right? Because just like we said that the error should get smaller as the graphs become easier to distinguish, as we get more infection observations, then also the error should get smaller, because that confirms our belief that it's equal to one graph or the other. So what you'll see is that if you do this m times, you end up with some factor of m in front of everything, which kind of agrees with the intuition you might want. Okay. So just to wrap up, I think, well, maybe both of these pieces of work feel like they're just sort of scratching the surface of something much bigger. The second one, maybe even more so. So in the second piece of work, we're really just trying to investigate what hypothesis testing might look like when we have different graph structures. We were able to come up with a permutation test and a proof that it works in the case when the product of the automorphism groups is a full symmetric group. And I should say that, well, there are lots of open questions. Maybe the first one that's not even listed here is, can we come up with a more interpretable condition? Because really, we've just come up with a sufficient condition which has to do with automorphism groups, but it's really hard to interpret. So it would be great if we could come up with another condition that were a little bit more interpretable, under which this method still works. Beyond that, even trying to figure out what graphs to use as null or alternative hypotheses in real life might be difficult. You can always imagine looking at a case where the null hypothesis is that it's a complete graph and everyone is symmetric, and the alternative graph is something that you might imagine, you might hypothesize based on domain information. Another setting might be where you have sort of, maybe you're looking at something like a gene network, and someone has proposed that the gene network is a certain graph, and you think that one of the edges or a couple of the edges should not be there. Then that could be a null. Right now, we're just sort of trying to fish around for something that seems realistic. And then also in the case of, in these settings, we have assumed that lambda and eta are homogeneous, because really the success of our method depends on everything being nicely exchangeable under the null hypothesis. In practice, you might know that certain edges are more likely to spread the disease than others, and it would be great to be able to incorporate that into our setting as well. So that's it. The first paper appeared in Transactions on Network Science and Engineering, and the second one is currently in submission. So thanks for your attention.
Thanks a lot, Po-Ling.
Mm-hmm.
Yeah, I have a quick question. So in the first part, would it be, because what I understood from what you presented is that the size of the set, your estimate of where the rumor or the infection started does not depend on how many infected nodes are, right? Yeah,
that's right.
And would it make sense to ask, so meaning if you have 10 million nodes or 10 nodes is the same?
Yeah. Mm-hmm.
So suppose I want to sample the red nodes to do the computation on them. Like, would so I have, let's suppose I can observe the affected node, but you cannot. But I want to tell you those nodes. So I don't need to tell you everything, right? So I just tell you the right amount. Let's say I'm allowed a budget of 100 out of 10 million that are infected, right? So is there a way? Is it an interesting question to answer? Sample these infected nodes such that I don't incur too much error on your side, because I see. Yeah, does it make sense, the question?
Yeah, that's interesting. So I guess one way to rephrase that would be how to calculate some estimate of the centroid of a tree where you only sample certain nodes in the tree.
Yeah.
Right? I think the difficulty in trying to frame that would just be, where would you sample? Because we're assuming you have an infinite tree.
Yeah, exactly. Otherwise you can skew, right? You can bias.
Right.
Because there must be some advantage of computing on a smaller number of infections. Maybe it's
right. I mean, if it's order n and n is the number of infected nodes, then you do want to do that. I guess, yeah, but you want to be able to sample so that you're still sort of central.
I don't know. That's what occurred. Yeah.
Yeah, it's interesting though.
Because somehow, like, it should be should be easier working on 100 nodes rather than 10 million. So
right.
Then how would you choose these 100 nodes? Like, I don't know.
Right. Yeah.
Yeah, that's it. So I guess I don't know if anyone else has a question. All right. So thanks a lot.
Okay. Great. Thanks for inviting me. All right. Bye.